So in this video, we want to find these following limits analytically. And so let's think about what kind of properties these various functions have, and that'll help us figure out strategies for evaluating the limits. So the first one is a cubic function that we're taking the limit of. And a cubic function, remember, they generally look like this, like that. And I don't know where x equals 1 on this picture, but let's say x is 1 like right around here. Right? Let's say that's x equals 1. Now, I don't know if it's there or if it's over here or what, but let's just say it's there. And one thing that we know about all polynomials are continuous everywhere. So since they're continuous everywhere, that means that around 1, if I come at 1 from the left side or I come at 1 from the right side, it's the same thing. Those values are going to approach whatever it is at 1, right? So that means that I can just say this equals the limit. Well, actually, I don't even have to say that. Since it's continuous, I can say that this just equals whatever the function value is at 1 if I call this inside part f of x right here, right? So if I plug in 1, I get 1 cubed minus 3 times 1 squared minus 2 times 1 minus 17. And so let's see, that's 1 minus 3 minus 2 minus 17, negative 21. So that's what that one equals. So if a function's continuous around where you're looking, well, then you can just plug in the value that you want right there, and it's good to go. That is the limit. So let's look at this next one. This next one's a little bit trickier because in this one, we're looking for the limit as x goes to 0, but I can't just plug in 0 because it's in the denominator. So if you think about, let's simplify the function itself. So this is the limit as x goes to 0 of, and then if I multiply out the top, I get 25 plus 10x plus x squared, and then minus 25 all over x. And then the 25s are going to cancel because one's positive, one's negative. And I'm going to get this, limit as x goes to 0 of x squared plus 10x, which is the same thing. If I factor out an x, I get 10 plus x all over x. So if you think about this one, well, if I call f of x, let's say f of x is that function, right? X, 10 plus x over x. Now, if you think about what this function looks like, those x's, they don't actually cancel, right? But the graph, if they did cancel, you can say that this function is basically the same thing as 10 plus x. The only difference is these x's right here, that's 1 at all times, except when x equals 0, the thing doesn't exist. So f of x looks like 10 plus x, right? 10 plus x, except for a hole at 0. So it looks kind of like this. And we're looking for the limit around the 0 there. We're looking at what value do we get as we come at it from both sides. And if you remember back in chapter 2, way back in the first semester, the way that we could figure out where that hole is by actually coming up with the extended function. And so that's not f, so I'm going to call it g, where we actually cancel out those x's, and so that's just 10 plus x. And g of x is the same exact picture as f of x, except the hole is filled in. Right? That's something that we learned last semester. So if I wanted to find the limit around here, right, what's that value where it doesn't actually exist and there's a hole there? Well, I can do the same thing just by plugging in the hole and then figuring out where that hole is, right, where that value is. And the way that we do it is by actually turning it into the extended function, because the limit of the extended function around 0, that's the same value as the one that has the hole there. So let's turn it into a function that's continuous. So if I cancel out those x's, I get 10 plus x. And now I've got a new function that has the same limit around 0. Right? So this one's continuous, so it's kind of like the case up here, right? 10 plus x just looks like this. So if I care about what it looks like around 0, well, then that's just the same thing as plugging in 0. So it's 10 plus 0 equals 10. Right? So let's look at the next one. So this next one's a piecewise function. And a piecewise function, I'm looking at the limit as x goes to 2. Well, the only place where this graph really gets totally messed up is around 2, or potentially messed up is around 2. So let's look at kind of what this does here. If x is less than 2, then I've got the graph of 3 minus x, which is going to do something like this up until we get to 2. And then, so this is 2 here. And when x equals 2, when x equals 2, the y value is 5. This value right here, if you figured it out, it's 3 minus 2, which is 1. So if I plug in the x equals 2, then I get 5, which is going to be way up here somewhere. 5. And then for x over 2, for all the values greater than 2, that starts out at 1, except there's a hole there. And then it goes up with a slope of 1/2, so kind of like this maybe. So that's what our function looks like. And what we're trying to do is figure out, well, what's the limiting value around 2? So that means, what's the value as I come at it from this way? What's the value as I come at it from that way? And if those are the same, then that's the limit as x goes to 2. It doesn't actually matter what happens at 2, just what happens around 2. So let's look at what happens as x gets close to 2 from the left side. And as x gets closer to 2 from the left, we're using that function, or that part of the function. So that's going to be 3 minus x. And if I plug in the 3 minus x by itself, that's continuous. So if I plug in the 2 for that, then I get 3 minus 2, which is 1. And then if I look at what happens on the right side, well, the right side uses the x over 2 function. And x over 2, right, that's a continuous function. So if I'm just looking at the right side of 2, that's the same thing as just plug it in the 2. So that's going to be 1. And since these guys are exactly the same, so the overall limit as x goes to 2, when I don't put the sign there, that means plus and minus, of f of x, that's going to equal 1. So this whole thing that we have here equals 1. So this equals 1. The third example is a little bit weirder. This one is an infinite limit. And remember, infinite limits, limit as x goes to negative infinity. If you think about what that means on a graph, that means I'm going way out this way. So there's a little implied plus here because it's coming from the right side. But since it's an infinite limit, the infinite limits, you can only approach them from one side. So you don't have to actually put that plus there. It's implied. So for this one, we're looking at square root of 2x squared minus 5 over 3x. Now remember, when you're looking at infinite limits, a nice trick to do, out at infinity, only the dominant terms of the numerator and denominator are the ones that matter. So we can turn this into the limit as x goes to negative infinity of the dominant term on top over the dominant term on the bottom. So that's root 2x squared over 3x. Now, root 2x squared, that's going to be the limit. Let's rewrite the limit part. So the root 2 is just root 2. If I take out the x squared, that's actually the absolute value of x, right? Because I don't know if x is positive or negative, but I know that if I square it and take the square root, it has to be the positive version. So I'm going to put it in absolute values there. And then the bottom is over 3x. Okay, so let's think about what happens when you plug in a really big negative number. So the root 2 over 3 stays the same. And the absolute value of x over x, well, if I plug in a really big negative number here and divide it by a really big negative number there, that's just going to be a really big positive number divided by the negative version of itself. So that's negative 1. So this whole thing is negative root 2 over 3. Okay, I hope that helps some.